Hey everyone, Mr. Fugate back for part two of sector area and arc length. So the first video placed an emphasis on degree measures. Our focus in this video will be on radian measures. Now, there's a clear option you have here in these problems, and that is if you are presented with an angle measured in radians, you can always use the degree conversion formula, turn it into degrees, and then use the formulas we used from part one. That is an option. However, the radian formulas that we're going to derive in the beginning of this video are actually more useful, number one. Two, they're simpler. And C, they have additional powers and applications that we can use beyond the confines of this geometry class. So I'm going to show you those new formulas. Now, what I'm going to do in the next few moments is show you how we can take our formula we've already worked with and turn it into that radian equivalent formula. So I'm going to take the theta out and put a d there for degrees, because what we need to do is we need to convert degrees into radians. Now, one way we can do this is we know that we can create a ratio of 180 over pi, and we know that that is equal to degrees over radians. So what I'm going to do is I'm going to multiply both sides by r, radian, and we get 180 r over pi, and that's going to be equal to my degrees. So if I take that formula, and I'm going to now take this and insert it here, we can create a modified sector area formula. So this is going to be pi r squared. Now, instead of writing it as a complex fraction, I'm going to separate and put the d in front. So d times 1 over 360. That's a little bit easier to look at. So we'll insert that 180. Now, we have to be careful with that r, because maybe I'll do rad for radians. I don't want you to think that's radius. It can be very confusing, so we need to really be careful with that. And then we still have the times 1 over 360. So how does this formula end up simplifying? Well, what ends up starting to occur here is that the pi's are going to cancel. 180 and 360 will cancel to be 1 and 2 respectively. And so when I simplify all of this, we're going to end up with an r squared. We're going to end up with a 1/2. And then we're going to end up with my radian measure, whatever that radian is. So we'll go ahead and reconvert that back to theta. So it'll be 1/2 r squared theta, and I'll put a little r down there just to denote that we're talking about radians in that situation. And so we take our original degree formula and we can convert it into this sector area formula. Typically, we'll just use the letter A for this. It's going to be 1/2 r squared theta, and once again, just to note, that theta is going to be in radians. So this is our brand new sector area formula, as long as we do radians. Now we're going to do something very similar over with our arc length formula, and this is really interesting what you'll see happen here. So we're going to take our arc length, we'll say 2 pi r. I'm going to move this in the front here, so we'll say d for degrees, and that's 1 over 360. Now it is time to go back over here, and we know that degrees are equal to 180 times your radians over pi. So we're going to take that and insert it in for degrees. So what do we end up with here? Well, we're going to get 2 pi radius, and then we're going to have our new 180 times radians over pi times 1 over 360. So what now happens here? Well, we have the number 2, we have the number 180, we have the number 360. 2 times 180 is 360, and then divided by 360 means that all of that cancels. What happens next? The pi's cancel. So what we're left with is r times your radians. And so our arc length formula boils down to simply r times theta, remembering that theta is in radians. So a much, much simpler formula here for us to denote arc length. Now, arc length is usually not abbreviated as AL. They use S to denote arc length. If you want to know why, you can do a quick Google search, but it has to do with the Latin for length. That's the reason why S is used. So this is what you'll typically see. Once again, that radian is going to be your theta here. So that is going to be our arc length formula. And so we're going to now use both of these formulas in the context of problems involving radians. So let's begin by looking at example 4b. So in 4b, we are given a radius of 36. So let's go ahead and let's try to draw in that 36. 5 pi over 6 is going to just be slightly less than 180, since 6 pi over 6 is 180. So if I want to draw something to scale, this is roughly what my theta is going to look like. So what we want to do first is we want to find our area of our sector, which our new formula now is 1/2 r squared theta. And from there, we'll go ahead and substitute those values in. So my radius here is going to be 36. My theta in radians is going to be 5 pi over 6. And when we crunch those numbers and we evaluate all of that, we're going to end up with a sector area here of 540 pi, and this was measured in meters squared. So that's going to be the area of our sector. And then lastly, we have our arc length. Arc length formula is just going to be r times theta, and we'll plug in both things. So the radius here is 36. My radians are 5 pi over 6. And when I multiply those together, keeping it, of course, in terms of pi, we're going to end up with 30 pi meters as our final answer. Now, one idea to note before we look at some other applications, the derivation that I went through back in this problem here, you don't need to replicate that. I just want to simply show you the idea that we had a formula that we were able to agree upon with degrees, and I wanted to show you how we can use conversions to then create that alternate formula that we can use at all times. Same thing goes here from degrees to radians as well. So that's really all you want to take away from those first 3 minutes of the video. So take a look at what you have here, and now what I want to try and do is look at a different type of problem, a different idea, a different concept, and we actually want to use the radian formula for this. So we have here a 19-inch pendulum, and it swings through an arc of 42 degrees. Now, I'm going to want this to be in radians because it's going to make my life easier when we use this formula in just a moment. So remember, if we want to convert degrees into radians, we would multiply by radians over degrees. So that's going to be 180 in the denominator and then pi radians in the numerator. And when I simplify that, we would end up with a value of 7 pi over 30. So that'll be the radian measure we use in a second. Now, it's saying that the pendulum, so here's the bottom of it, is swinging 42 degrees. So it's going to basically swing from there to there, creating that 42-degree angle, which we now know is 7 pi over 30. We want to figure out this distance right here. That distance is going to be our arc length because it's traveling on the outside of this circle. So if I were to really swing this all the way around, we would create a circle, as I just created sort of something there. Let's go back to full screen. As I was drawing outside of that, we would create something like that. But we only are swinging it 45 degrees. So we're going to use our new arc length formula, which is r theta. And so my radius here is 19 inches. That's the length of the pendulum here. And then my 45 degrees as a radian is going to be 7 pi over 30. So what I'm going to do in my calculator is we're going to take 19 times 7 over 30. And when you do that and you simplify your fraction using whatever method your calculator will work with, I'm going to get 133 over 30. So my arc length is 133 over 30. The approximation of that is going to be roughly 13.9 inches. So if you write it in exact form, it's 133 pi over 30. Our approximate answer is going to be 13.9. Let's take a look at one more example of this. So now we have something a little different that's interesting here. It says you're sitting on a merry-go-round that completes a revolution every 10 seconds. This is going to be a little bit of a challenge, a little different. The horse is 18 feet from the center. That's going to be our radius, by the way. We want to know how far we traveled on a 2-minute ride. So let's mark this as my radius. And then we want to know how far we traveled in a 2-minute ride. Take a moment and pause this. This is a challenge. I want you to think about what your theta is going to be in this situation. So if we're traveling 1 revolution every 10 seconds, another way I can think about this is I would do 6 revolutions per minute because there are 60 seconds in a minute. And because we're on a 2-minute ride, we would actually make a total of 12 revolutions per minute. So this is interesting because when we talk about our theta now, okay, that means we are going to start here and we are going to rotate 1 revolution, 2 revolutions, 3, 4, and so on. And we want to take that entire green segment that I had scribbled up there on the screen and basically lay it out and figure out how long, how far I've actually traveled. Well, one revolution, as we know, is going to be 2 pi radians. So if we're going to do 12 revolutions, well, that's just simply going to be 12 times 2 pi, or 24 pi radians. This is going to be our magic number, and this is going to be our theta for this problem. So now we can set up our arc length as S equals R theta. This is part of the reason why I like this formula better, is because it makes more sense. It's a simpler formula when we have multiple revolutions. Maybe we're talking about bike wheels rotating. And instead of having to look at it from a pizza slice perspective like we did in the first video, this is a little bit simpler once you get the idea of what the actual total amount of degrees, or I'm sorry, total amount of radians that we're trying to look for here. So to get that arc length, we'll put our radius as 18. Our radian measure is going to actually be 24 pi this time. And so all we have to do is multiply 18 by 24, and we're going to get an answer of 432 pi. This is feet as it's measured. If you wanted to get an approximation for this, all we would have to do is multiply that by pi, and we would get about 1,357.2 feet. So either one of these perspectives that you can look at, that would be the total distance as we go around this merry-go-round, a total of 12 times. And I just noticed, I should say per 2 minutes, by the way. So that will conclude this video and this final example. So now we want to take this and try some practice with radians, and in addition, try some application problems. Thank you for watching.